I'd like to introduce you to a very interesting synthesis technique that's inspired by speech production called Vosim. It's fun to play with. It's very simple. It's pretty fast and efficient. And let's take a look. As I said, Vosim was inspired by the voice. It was developed in the 70s by KG and Templars. And the basic idea of Vosim is to think about what happens when a glottal pulse hits a resonance. So remember, glottal pulse means one pulse coming through the vocal folds or the glottis, and the resonance is a formant, a resonance in the vocal tract. And what happens in the time domain? Well, the answer is you get an exponentially damped sinusoid. So of course, in speech production, we have multiple formants. Remember those two formants in the graph that accounted for most of what makes different vowel sounds. So those were two resonances, and so when the pulse hits a complex filter with multiple resonances, you essentially get the superposition of these damped sinusoids. And the exact details are influenced by the shape of the pulse coming in and other factors, but let's start with this damped sinusoid idea. In true Vosim, we don't use a damped sinusoid. We use a pulse train of sine squared pulses that diminish in amplitude. I believe that this was done for some computational efficiency and numerical reasons, but the graph here shows what a one period of Vosim looks like. These pulses here are formed by squaring a sinusoid, and so you notice that they're all above zero, which is a characteristic of Vosim. And the parameters of Vosim are that we have an initial amplitude A, we have a frequency, or the period, which is T. We have a decay factor. So each one of these pulses is just the previous pulse multiplied by a decay factor, which is also interesting. So it's not a continuously decaying, but it's kind of an approximation of continuous decay by only multiplying each pulse by a factor. And so these pulses diminish, and we synthesize n pulses, and we follow that by a duration of m silence. All right, so we're actually constructing a period of a waveform from these components, sine squared pulses with decay, and we do n of those and add some silence. So this is, in spite of the somewhat ad hoc nature of constructing this waveform, it does behave pretty much like an exponentially decaying sinusoid, and so it does give rise to a spectrum with a strong resonance or strong peak. And of course, the peak frequency is going to be the frequency of these pulses, but the fundamental frequency will be the entire period from zero on the left to the end of the period at the right. So that determines the fundamental frequency, or the pitch, and the rate of these pulses determines the resonant frequency. So I think you'll hear that in some examples. So let's see, I've talked about how these different parameters influence the signal. On top of that, in the original Vosim paper, the Templars added various delta or increment parameters to get the signal to change over time. So rather than using continuous control of parameters through some envelope, there was discrete control saying, okay, the pitch is going to increase because every period we will decrease perhaps the m period of silence by a small amount. There's some example code for Vosim in this file vosim.sal. And also I can play some sounds of various Vosim examples from YouTube, and you can go watch the entire thing yourself. Here's the URL. So let's take a listen to some Vosim.